Good afternoon, good evening, depending on where you're joining us from today. My name is Chuck Tatham. I'm the Chief Revenue Officer here at Densify, and I am joined by Mr. Andrew Hillier. We're pleased to be here today to talk to you about a rapidly rising issue that we're seeing in many enterprises that are running at scale with Kubernetes and containers, and that is specifically the occurrence of containers and infrastructure where resources are not specified properly. It sounds like a crazy thing, but we're seeing a lot of it. Andrew's going to talk you through what that might mean and why you should take it seriously. That's largely the focus of the content today.
I'm Andrew Hillier. I'm the CTO and one of the co-founders of Densify. And like Chuck said, I'm going to go keep it brief. I'm going to keep it technical. It's going to be very much to the point. And today is the dangers of unspecified resources. There's dangers in not properly specifying resources. And today we're talking about what if you don't specify them at all. Before I dig in, just a quick note on who we are. Densify, we're really analytics, and we really target and focus on cloud-based, cloud optimization, container optimization. So if you're heavy in the cloud, it will precisely optimize the resources across the major cloud providers, and of course, containers and Kubernetes and variants, EKS, OpenShift, things like that. So I'll try and talk a little bit more about that as I go through. But if you've got containers, and especially if you have containers running in the cloud, the things I'm going to cover are probably highly relevant to you. So let's dive right in. Let's start off with the container resource challenge. So with containers, and here's a pod spec where we're trying to specify a couple of containers here, and you see they have all these values. I will try and cover things a bit from basics in case you're not overly familiar with this. For each container, you have to tell it how much CPU and memory you want and what the limit should be. So requests and limits on what you're getting. And somebody needs to do this. One of our other webcasts, I cover this in great detail. And the analogy I give is kind of like on my laptop, I had to tell my laptop how many millicores of CPU to give PowerPoint or Word or whatever I'm running. It's very difficult to do. It's not something that people generally think about or know, and it's at such a highly granular level that you have to do this across thousands of containers. So invariably, it's very difficult to get right. I'll give a couple of examples here. So what we often see is if this is the CPU utilization of a container, and this is a 24-hour view, and that curve, the kind of candlestick chart, is showing the CPU utilization of that container, the peak, the minimum, and the fat zone is kind of sustained activity, where it's spending its time. And you can see this one's hovering around, upwards of 500 millicores, peaking at 750. The dotted line at the top, the yellow line is the request value, and the purple line is the limit value. And in this container, they happen to be set to the same value. So this is a case where I'm asking for 2 whole CPUs for this container. I'm not using any of that. I'm barely using half that. 367 is the average. So we're asking for way too much resources. The technical term we give is way too big for this one. I'll talk about the implications of that in a second. Here's another case. It could even be the same container. Here's memory where we're asking for a gigabyte of memory and it's using upwards of 3. This is very common. We see this happening in all directions. Too big, too small. I'll talk about not being set at all in a second, but just to kind of talk about the implications of this. If you set things way too big, then what happens is Kubernetes will start stacking up the containers on the nodes, and I'll talk about this in a bit more detail. And in this case, here's a real example. Here's a real running cluster from earlier this year, it looks like, where the request values are taking up 80 or 90% of the cluster resources, which is great. So Kubernetes is giving out CPUs to all the containers and pods, but the utilization is down, averaging around 7%, because they're just way too big. You're asking for resources, and the way Kubernetes works is once it gives you the resources, the admission control won't let anybody else on a node once you've given out all the request value. So what happens is you end up with these really low utilization levels. If you're used to something like VMware, that overcommits. Kubernetes doesn't overcommit the same way. It won't keep giving the same resources out to multiple consumers. It'll just stop when it's giving out the nodes of the resources. You can steal from each other at runtime, but when it's starting containers, it makes sure there's enough resources on the node to fulfill the request. So the other way to put it is that it's not giving out virtual resources. Kubernetes works in real resources, and it's giving out real millicores, and you'll end up giving it all your resources and having very low utilization. So this is a big pain point we see. Not everybody's aware of this because not everybody kind of clicks down at this level to see this happening, but it makes your containers very expensive.
Admission control is a cool name.
It's a good way to think of it because containers steal from each other at runtime. You can go over your request, you can't go over your limit, but when it's admitting them, it doesn't let you in unless it can guarantee you've got the request amount of resources. So again, a lot of people overlook that because they come from a VMware background where you can give the same CPUs out 8 times if you want to. So that creates one business pain. That's not the pain of today's discussion. Let's move on and talk about things being too small, which also isn't really the topic of today, but it's highly related. If I make the memory request values too small, and this is just some OpenShift documentation because it kind of, it articulates it well. If you don't request enough memory, then Kubernetes will keep stacking containers on nodes, and the utilization might end up exhausting the node's memory. And what happens is the out of memory killer will kick in and kill you. And that's kind of scenario number one, where things get killed because a node is out of memory. If you go over your memory limit, the CPU behaves differently. For memory, if you go over your limit, something inside your container will get killed. The Linux kernel will actually kill something inside your container. And that's particularly evil. We've seen that happen where if your limit's too low, then it's just going to stop your container, stop things from running inside your container to make sure you stay within your limit. And all kinds of weird behavior occurs. That's too big. This is too small. Again, this is not the topic today, but it's highly related because these things can also happen if you don't set the requests and limits. One of the things we did, we worked with customers quite a bit on this in very large environments, 50,000 containers or more. And we realized that it's a very good to visualize this because there's so many moving parts and so many settings, it's hard to wrap your head around it. So what we did is we said, okay, if we have a condition like this where we have a container that wasn't given enough memory, requested 1 gigabyte and it's using 3, we can actually plot that on a histogram saying, well, that's kind of in the red zone, it's a danger zone, and it's about a third of what it should have. Another example, here's one where we're giving it 500 megabytes, it's only using 100 megabytes, so it's way too big. We can put that over in this bucket where it's 5 times bigger than it needs to be, and start to build a picture of what's going on. Maybe here's a third container, and this one looks pretty good. The yellow line is around 750, 760, and we're using about 750 or 40, it looks like at peak. This is a great configuration. That looks like the way it should be. Let's put that in the green right on the center line. We see things too big, too small. They can be just right. Or more to the topic today, here's one that doesn't have a green or a yellow or a purple line. You didn't tell it what you want. And I'll talk about what happens when you do this in a second. But we can visualize that too. That goes off in this unspecified section, kind of off the end of the red, because weird things can happen when you do that. And if we take this paradigm and kind of do it for a whole environment, you can do it for an app or a line of business. Every container you own, we generated this for 50, 60,000 containers. The shape of it is very revealing, where you see that you got some stuff that's good, some stuff that's under configured, some things that are over configured, the yellow, and of course that gray zone where things aren't even set at all. Visualizing this, we found to be extremely helpful because container environments can be very large, and even if not, again, there's a lot of moving parts and they're very complex. So with this, it's like an ink blot test saying, hey, I actually have a good picture of an environment just by glancing at this chart. We developed this, we run it in our customers, and again, we can get very rapid visibility into what's happening in the container environments. And here's an example of that. This environment has about 15,000 containers. We call this a 4-pack. So the top left is the CPU request values, top right is the memory requests, bottom left CPU limit, and then memory limit. So I can see all 4 specifications kind of across the board for my whole environment. In this case, all the containers that are running in a specific CSP. I think this was Azure in this case. You can start to build a picture. So almost a third of the containers were given way too much CPU, like way too much, 5 times too much. Now these could be tiny, these could be big. You can drill down and see what that is, but they're wrong is the main point. So you're giving out way more resources. That causes that cost problem I was talking about. At the same time, almost 1,000 containers have a fifth of the memory they need. Now, luckily, there's yellow in the memory. So you're also making some containers way too big, and you might be getting lucky that the ones that are under configured are just stealing from the ones that are over configured. And if they're getting put on the same nodes, you get lucky. But you might not be getting lucky, and things might be going horribly wrong. So that kind of spread means you might on average look pretty good, but when you open it up, things are wrong in all directions. And we see this everywhere. And you can plot this right down to, I can just look at my Nginx or my MySQLs or whatever. I can generate this for an application as well, which is kind of cool. Getting more to the point, you see there's memory risks here. There's memory limit red, which is very bad, but there's also gray down here. And that's really what I want to talk about today. You didn't specify a memory limit. So you are not capping the containers. They can get a memory leak and grow out of control and cause all kinds of bad things. So you see this environment's not too bad. There's not a lot of gray in the CPU, the request values. There is no limits in the CPU limit, and there's quite a bit in the memory limit. They're just not being set. I want to dig into what happens when you don't set things. So let's start with the CPU request. So that top left curve is the CPU I'm asking for. If I have a really big app, I might ask for 4 CPUs to make sure I get enough when it gets busy. And let's talk about it in terms of these charts. So it's that yellow line that I was showing earlier. So here's a CPU utilization chart in millicores, and we're asking for just over 3 CPUs. So it looks like the way you interpret this curve is that it doesn't really go much below 1 CPU It's got, the floor is not down at the bottom, so it's got sustained activity all the time. And in the middle of the day, okay, let me do it 3. It goes up, uses 3 CPUs and upwards of almost 5 CPUs. So we don't want to request the very top of that curve because that might just be wasting resources. You know, the policies, we have tunable policies that say where in there you want to actually target your request values. If you don't set that and there's no yellow line, what happens? Well, first of all, what it defaults to is that purple line, the limit value, which will just make it really overspecified. So if you set a limit but no request value, it will fall back to the limit. That's going to end up costing you a ton of money if you use that a lot. If there's no limit, so there's no values at all, then what happens? Let's look at a node. Let's say just pretend there's a Linux node with a bunch of pods running on it. They've all requested CPUs, and they're using up most of the node has been requested out, but there's a couple of CPUs worth of resources left, unrequested. This is not utilization. Utilization could be 0. Utilization could be over this. This is divorced from utilization. This is just the requested values. There's still a bit more on this node to give out. I can't, Kubernetes, when it goes to start this container, if I didn't give it a value, it doesn't have any idea what kind of resources this thing needs. It hasn't seen it operate yet. It hasn't seen any utilization. It can't read minds. So it's going to say, well, you can fit. I think there is defaults. You can set up defaults to be like 100 millicores, I think in some schedulers, something very small. But what happens is it's going to say, hey, I've got 2 CPUs, 2000 millicores free. This thing isn't asking for anything. So, you know, I have no idea what it's asking for. Let's assume it fits. And it will get put on the node. And again, it won't get placed based on utilization. It'll get placed based on what's called the priority. So it'll get put on there and a new pod will appear. And then it'll kind of surprise everybody when it does whatever it's going to do. Just 1 second on these priorities, because I think they're important. Least requested priority, oh, sorry, there's supposed to be most requested priority, supposed to be the second one there. They will either spread things out or stack them up bigger. So if I've got a bunch of nodes and they're always running, I probably want to spread things out for performance reasons and let them fill up evenly. If I'm running in a cloud with a scale group or a scale set, I probably want to use the most requested, which is, there's a typo here, I don't have most requested, meaning it'll fill up nodes first before it moves on, because that gives it the highest likelihood of being able to turn nodes off when things get less busy. It kind of concentrates the pods, and hopefully nodes will become idle and then can just be turned off. That's what it uses to place them. It doesn't monitor the CPU utilization. It doesn't even know what you're going to be doing, so it couldn't use it even if it wanted to. So it's going to start you based on one of these algorithms. In this case, what happens is when that lights up, when the workload gets busy, it's going to go well over what the resources left were. There's only 2 CPUs left, and this thing is going to hit almost 5. So you could have an issue and cause contention. And then in that case, things will get throttled. Again, back to your laptop, it's like when things all run at the same time, your fan gets really hot, you know, the thing is hot and the fan goes off. That's what's going to happen on the node. They're elastic resources, so they will just, you know, throttle each other. Nothing gets killed, but it's not going to perform very well. Not telling you what you need is, Kubernetes has no idea. It's a bit of a crapshoot. It's just going to put it there based on what the requested values are and hope for the best. CPU limits. This is a bit different. So if I don't specify that limit up there, then Linux can't limit you to a specified amount. So if you do set a limit, it'll say, hey, container, you're running hot. I'm going to stop you from taking any more resources so you don't mess anybody else up. So if you don't set it, you won't get throttled. It's not overly dangerous because then you'll just use more CPU, and then if the whole node gets saturated, fan starts going and you get performance problems. But it's kind of like a typical system. It'd be like your laptop where things get busy and they might run into each other or they might not. So we actually see customers not setting the CPU limits because it's not the end of the world. It's nice to throttle things, not get out of control, but if they get out of control, it's not the end of the world. It takes quite a bit to saturate the CPU of the entire node before things go wrong, and it might only happen for a short while. And I should mention that you can set default. So you can say, I don't want to set limits on individuals, but I can set a default limit across all my containers. It's not overly meaningful because there's not really one number that is going to make sense for all the containers, but it can be defaulted. So at least everything has a limit. It just might not be a very useful limit because things might regularly exceed that. You definitely don't want the default limit to be small, or you're just going to throttle all your resources. Memory requests. These ones are a little more nasty. So here's an example of a memory curve. The request and the limit are both set to about 5,500 megabytes, 5.5 gigabytes, it looks like. So they're set to the same value, which in this case might make sense because it's a pretty flat workload. If you don't set the request, it'll use the limit. If you don't set either, then it has no idea how much memory you're going to use. And like CPU, it's going to say, well, I've got a node with 2 gigabytes free on it. I have no way to know if there are sufficient resources available on that box. So I'm going to say, hey, well, you didn't tell me what you need for memory, so I'm going to assume you fit. There's 2 gig left. That seems like a lot of memory. Let's start the pod. And again, it's based on just what the configurations are of all the pods that are running, not the actual utilization of what's on that box. And it has no idea what your new thing is going to do. So it just starts it. And when the workload lights up, so when you actually start your thing, that pod, when it starts using memory, like I mentioned earlier, you can't throttle it. It's not like this thing gets big and they all slow down. You can't share memory. The other memory killer kicks in and kills something on the node to stop the node from running out of memory. Now, it will kill the thing that is the highest over its request, which hopefully is the thing that's growing. It might not be. Back to the histograms, if you have a lot of containers that are misconfigured and the memory's in the red, they could get killed. It's going to try and kill the thing that it thinks is going. But again, if you have the requests are all wrong, it might get that wrong and it might kill something important. That's kind of a nasty scenario. If I don't give a memory request, if the request is too high, it's going to waste you a lot of money. If it's too low, or in this case, if it's not set, you can blow things up. We've seen this happen in customers where there's nodes are out of balance and one of them gets saturated and something gets killed. Memory limits, I'm going through that 4-pack that I was talking about. So this is the maximum amount of memory I want the container to be able to use. It's the purple line here, but it's hard to see in this one. If you don't set it, then Linux can't enforce a limit. Also, not like CPU limits, not setting CPU limits, you might be fine. Not setting a memory limit is very dangerous. And we've seen this happen where you get a memory leak in your container, it just marches on and blows up an entire node. I described that on the previous slide as well, but this is a very direct case where I'm not limiting. Again, it's similar. The pod grows. I didn't bound it in any way. It'll just end up using 128 gig or 256 gig or whatever it gets to. We saw a cool case where this was happening over weeks. It was a slow ramp where this one pod was just losing a bit of memory every day. And we caught it about 4 days before it hit the roof. And something would have gotten killed in a production environment. Again, the limits, memory limits, they're more dangerous not to set because you're just not limiting anything, and programming mistakes, bugs can cause instability in the container environment. That's kind of a fairly detailed walkthrough of the 4 areas. They're too big or too small, it causes different problems. If they're not set, it causes very specific risks based on the behavior of Kubernetes. Again, you can default things, but that's not overly useful because there aren't really good defaults to set. The name of the game here is let's fix this. So here's some analytics that's just kind of showing, I've been showing snippets of this, where when you analyze a bunch of containers, this is drilled right down to the detailed level. Some should be bigger, some should be smaller, some should be both bigger and smaller. I won't go into all the gory details of the recommendations, but some things might have too much memory and too little CPU. This one, for example, it needs to be made bigger, for example, resized in different ways. And this is what you see, the curves across the bottom, or in this case, the request needs to be brought down. But you see the third row down is one that doesn't have a specification. And we're recommending it have one, a pretty big specification. So you didn't request any value, but it needs 5 CPUs. It's a big workload. So it's important to kind of get those numbers correct and then set them into the environment. And so if you see this kind of all these numbers, there'll be thousands and thousands of numbers generated. It doesn't make sense for humans to be doing this. There's too many moving parts and too many workload curves and to figure it out. So here's some analytics.
What's one of the largest container environments you've seen, just for fun?
Personally, I've seen this with about 60,000.
Can you imagine trying to keep track of these kinds of settings on a 1-by-1 basis? Almost, it's just not even conceivable.
Even if this had 20 rows in it, you can't really do that, because if you go down here, there's all these details and policies, and it's not just these 2 curves. There's a CPU of a typical day, the CPU of the busiest day. There's different policies that come into play to understand the curves to make sure you're getting the right numbers. So to come up with that number is actually quite complicated, and you want to filter out spikes where things might use a lot of startup but not steady state. So there's a lot of math in here that we do and a lot of policy elements that come into play to make sure that you get the right engine or the right numbers.
And of course, all of this comes together to impact the nodes you select or the eventual efficiency of the infrastructure, right?
Absolutely. So if you over request everything, then the nodes will get started and they're not utilized very well, and you'll end up running way more nodes than you need, and your bill is huge. It all filters through the nodes. The unset values, all kinds of either cost or risk can occur. The unset values here contribute heavily to that. Like again, this row that's showing here, you've got a workload that's going to use a ton of CPU. You didn't ask for any. When it throws it on a node, who knows what's going to happen? You better hope there's some massively over-configured containers on that node that can sop up the utilization, because otherwise you're going to have a big problem. And again, even just doing a handful of these doesn't make sense to do it by hand. So here's a view of the actual analysis, and then just a kind of a customer example of this where this is their pipeline. I'm not going to get into all the color coding and details, but what they do is do this analysis on their environments, so all their environments, not just prod. And then at the time they're building the images, they just hit the APIs to get the ideal requests and limits through some really cool sounding software. They will update, in this case, the OpenShift templates automatically every time. And they don't need change approval for this. They negotiate, they inform change management, but they don't need an actual approval through Jira or ServiceNow. So every time the containers go out, they are optimal. It's a beautiful thing, and they have one of the nicest histograms that we've seen. I do believe there is a bit of gray in this environment. This isn't showing any gray, but as things come online, the gray might exist for a little bit, and then it gets smacked down because everything gets a value. And this green bar being high, I like to joke, it's kind of like giving the finger to cost. Things are really good. The only reason it's not all green is because the recommendations don't make too drastic a change. You don't want to take away 9/10 of the resources of a container. It does it in slower steps. Next time around, it might do a little more, so it'll kind of iterate towards the right answer without creating too much volatility. So this is kind of a beautiful case of analyzing automatically and just having it happen in an automated way in container environments. And the developers can focus on functionality, not millicores and megabytes.
A question, Andrew, where does the data come from?
Prometheus in this case. So Prometheus is, we find, the de facto standard. So there's a forwarder that will just run somewhere in your environment, will grab the Prometheus data and some node exporter data, and it'll fire it to the Densify SaaS service. So it's really simple to set up. Data just flows over, so through a forwarder. So yeah, we find Prometheus very commonly in use out there, and that's what we leverage. We did another webcast where I went through this whole table, not as much detail as today, where the different CPU and memory requests down the left, and what happens if they're too big or too small or not set, and whether that's a cost or a risk problem. And as I covered today, if you don't set them, all kinds of weird and wonderful things can happen. You can overstack, you can have performance risks, noisy neighbors, that type of thing. And the same is true for all these other cells. And I'll just leave this for reference. There's an entire webcast on this topic where we go through these in more detail. And I alluded to some of them, of course, the yellow and the red zones. But today's topic is, if you don't set the values, not setting CPU limits isn't the end of the world, but the other ones, they really should be set. And of course, they should be set to a good value as well. One last note in 30 seconds, Chuck alluded to this at the beginning. We have a great relationship with Intel, and Densify is actually offered as Intel Cloud Optimizer and funded by Intel for qualifying enterprises. You can use it, you can analyze the cloud environment, see these pictures, see this stuff in your own environment. So we just want to throw that up if you're interested. There's a QR code there. And with that, I will stop talking.
So Andrew was talking about some of that content. The resources section of our website can give you access to those recordings as well as guide material, which is packed full of useful info. We also ask you to reach out to us if you have any further information requirements. But thank you all for your time. Thank you, Andrew, for this content. And everyone, enjoy the rest of your day or evening. Thank you.
Thanks, everyone.